So, we're working with Descartes' rule of signs. It was invented by René Descartes, lived about 400 years ago, a very brilliant French mathematician. He also created the Cartesian plane, the coordinate grid that we use, with the origin and the two axes. He develop that as a tool for map making. Legend is he discovered it while watching a fly crawl across the ceiling tiles. Anyway, we're supposed to work on the rule of signs today. And this is going to tell us how many possible, just as it says on the chart there, positive real roots and how many possible negative real roots. And the real roots is going to include square roots, cube roots, irrational numbers like pi. It will not, however, include imaginary roots. And that's why it says on the chart, once you find the answer, keep subtracting 2's if you can, because maybe there will be some imaginary roots that aren't included, and the imaginary roots always come in pairs. To set up the problem, we put the problem in descending powers, like we're used to. And it does not matter if there are certain terms missing. It does matter if there is a common factor. So if we had something like f of x equals 6x to the 6th, the fact that we're missing some places doesn't matter, like it does in division. Synthetic and long division, you have to do the place values. But if there is a common factor, we will have to take that common factor out. And there is a common factor of 2x squared. So we pull that out first. And then we find, because 2x squared is a factor, that means that x equals 0 is a root. In fact, x equals 0, because it's x times x, is a double root. So how many roots would you expect for this polynomial? If it's degree 6, it should have 6 roots. And that's a fundamental theorem of algebra. 6-degree polynomial should have 6 roots. We already know what 2 of them are. So for this particular problem, we would only be looking at this part here, like the depressed polynomial. So we're going to use we're going to use the rule of signs on this part right here. We're going to let f of x equal 3x to the 4th minus 2x plus 1. And we count the sign changes. How many times, some textbooks call it the variation in sign. So we start with a positive, and then negative, that's one change. And then this term is negative and it changes to positive. So there are 2 changes. So this would indicate there are 2 possible positive roots. Or step it down by 2, there are 0 possible positive roots. So maybe the whole thing is going to intersect the x-axis in 2 positive x values, or maybe no positive x values. To find out how many negative roots there are, we put negative x in for x. And count the changes. So we're going to start with the same thing here. And put a negative x in. Well, if you put a negative x in here, raise it to the 4th power, it becomes positive. Multiply that times 3, it would still be a positive. If we put a negative x in here and multiply it by negative 2, that's going to make it a positive 2x. And the plus 1 is still plus 1. And then we count the changes. Well, this is positive, and it's still positive, and it's still positive. There are no changes. Which tells us there are 0 possible, negative roots. So if you did a whole rational roots theorem on this, and got a list, plus and minus this, plus and minus that, plus and minus that, forget the negatives. None of them can work. It is not possible for there to be negative roots to this. So to summarize it, and they sometimes do write little charts like this, it was 6th degree, we had 2 roots that were x equals 0. They're not positive, not negative, but they're still real. We had the possibility of 2 positive roots, or 0 positive roots. We had no possible negative roots. So we could have 2 positive and no negative. We could have 0 positive and no negative. And we already have used up 2 roots. So these two positive, no negatives, that would mean there'd have to be 2 imaginary roots. We have the 2, 0, x equals 0s, no positive, no negative. That would mean there'd have to be 4 imaginary roots. So let's try some from your textbook. Going to use some from page 138. If you could please find page 138.